Hi everyone, and welcome to your last module. In this lab we will explore a POC using an encryption algorithm. And okay, let's begin. We must go to module 9, lab number 1, and here it is. Let's open a command prompt. We click in this bar and type cmd. Okay, so now let's execute the program. And it tells us that we need to provide also a file path. We have a txt file greetings. Let's see the contents, and we notice there's a message hello, right? So now let's provide the POC this path greetings, and okay, this generates another file greetings.txt.enc. If we try to see the content of that file, there's a lot of seems like garbage characters. Okay, so in this folder we also have a ransomnode.txt.enc. So we know it must be the output for this program from a clear text file ransomnode.txt. Okay, so let's analyze this program and try to see if we can recover the original file. Okay, since this is a compiled program and not a script, we cannot simply open this program with a text editor. We must use something called disassembler to actually see what are the instructions that this program does. Okay, so let's open our disassembler Ghidra. We must go to the folder where we download it. So in my case it's documents, this folder, Ghidra, and here we can find a Ghidra run.bat. We execute it and wait for the program to show up. Okay, now the program has just started. We close these tips, and to start using it we must create a project. We click File, New Project, a non-shared project. Next, the project directory can be anything actually. For project name we will choose module 9 and click finish. Okay, so now we have an active project, and now we can start importing some files. So we click File, Import File, and we look up for our program. So we go to Desktop, HackDev, Model 9, Lab number 1, and our POC. Okay. So now Ghidra starts parsing the file. It identifies it's a portable executable. We click OK, and it starts parsing all the metadata of the program. Great, so now we must allow access to our Java development kit. Allow access, and now we have a summary. This is a POC. It's for Windows, and okay, we click OK, and now we can start disassembling the file. So we double click, and now it's launching the main disassembler. Now we are prompted with a message asking if we want to analyze the program now. We click yes. We stay with the defaults and click analyze. Great, let's maximize this window. So now Ghidra is analyzing our program. In the meantime, let's talk about all the sections of Ghidra. Okay, so this middle section is our main section where we can view the disassembly. Here are the opcodes, the address of the opcode, and the actual instruction. Here we have a summary of the sections. We have a symbol tree. We can view the imports of the program, the exports, the functions defined, classes, namespaces. In this part, we can view data types, built-in data types, or data types defined by the program. And here at the right side, it's the compile view. Here, Ghidra tries to reconstruct a C version of the code. This is very useful, so let's extend it a bit. Okay, maybe less. Okay, great. So now let's just wait for the analysis to finish. Okay, so now the analysis has been finished. We could start analyzing the entry point of the program and from there start reversing all the flow. But we found most valuable to begin identifying if this program uses some crypto API. So let's go to imports. We analyze this DLL and we can identify some crypto API, crypt acquire context, and so on. For a program to be able to encrypt or decrypt something, there's a series of APIs that must be called. They must called crypt acquire context. We must use crypt import key or crypt gen key, depending on if the program is generating its own key or importing an already defined key. So in this case, it's using crypt import key, meaning there's already a key somewhere. And well, crypt encrypt to actually encrypt some data. Of course, crypt destroy key destroys the handler for the key, and release context release the context already acquired. So let's begin inspecting the calls to crypt import key. So we click on this function and now we can see the import table, and most importantly we can view the references for this function. We double click and now we can view the function who is calling crypt import key. Okay, so for crypt import key, the second parameter is where the actual key blob is stored, and the third parameter just tells us how long is it. So if we wanted to know what is this key, we should do some reversing starting from this second parameter and going backwards, trying to identify where this value is actually being defined. Okay, so this is I think the most critical API call. After that, it would be crypt encrypt. We go to check the references, and well, we can view it's already encrypting something. Okay, so now how do we know which algorithm this program is using? Well, that info mostly comes from the calls to crypt gen key, but in this case, since the key is already created, we must have access to that key blob to actually tell if it's using RSA or AES or something else. Okay, so let's now retrieve the key. Okay, we have several paths, of course. We could do some static analysis, reverse engineer all the flow before crypt import key, and figure out what is the value of that second parameter. Another approach would be to load this program into a debugger, place a breakpoint just before the call to crypt import key, just before this call, and inspect what is in this second parameter, which is the register RDX. Okay, so we can use our tool NeZa. Let's open a terminal. We type cmd and navigate to our folder that is at desktop, hackdev, tools. Okay, now we call to neza.bin.exe, and we must provide a path to the program and all the arguments that program needs. Since our POC requires a clear text file, let's create that file in this folder first. So let's write something like by to content.txt, and well, now we can execute neza.bin.exe and provide the path as model 9 lab number 1 POC, and now the path to the clear text file, that is content. And now we must specify our tool that we want to intercept all the calls to the function crypt import key. Okay, for that we specify API hooking and the name of the function crypt import key. Okay, so now what's going to happen behind the scenes is, well, NeZa starts the program, intercepts all the calls to crypt import key, and in every call it will review the second parameter and dump all the content into a file for us. So now we hit enter, and great, so we identify a call. Here is the key data length, and that data was written to key.tmp. So we list the contents, and here it is, key.tmp. Great. We can inspect that key using cert util -dump and the key. Okay. And well, now we can see the algorithm type is RSA, and also we can notice this is a private key blob, meaning this key has all the parameters needed for RSA to decrypt whatever the public key encrypted. Remember, for RSA it's an asymmetric encryption algorithm, meaning there's a private key for decryption and a public key for encryption. In this case, this program had embedded the private key instead of the public key, and well, use that key to generate the public key and encrypt the file. So now we can use this key to decrypt whatever the program encrypted. We can write a tool that is RSA decrypt tool. We must provide the path to a key blob file, that is key.tmp, and the path to an encrypted file, that would be content but with the extension .enc. Okay, we hit enter, and now we can see the clear content of the file. Great. So let's use this key to actually decrypt the ransom note. So we go to the previous folder, module 9, lab number 1, and ransom note. We hit enter, and great, now we can see the clear text. This is a test ransom note, all files encrypted. Note created January 1st, 2025 at this hour. You can submit this to earn your points. Good luck.